Hello and good morning friends, welcome to CEC-UGC live lecture. Dear friends, with another lecture on Operation Research, today we are going to discuss more on Big M method. And for this we have again with us in our studios Dr. Subhash Kakkar. Dr. Kakkar is an eminent personality in the fields of academics. He has a vast professional experience too. So taking advantage from his experience in both the professional as well as academics field, I would like to introduce you once again to Dr. Kakkar, who is with us in our studios.
Hello.
Welcome to the EduSec lecture, sir.
Thank you.
And today we are going to discuss on Big M method. So over to you, sir.
Thank you, Gitika. Hello viewers. Today we shall be discussing Big M method under operations research. Under operations research, viewers must be knowing linear programming problems and how to solve them. And these kind of problems are solved by using simplex method and graphical method. Linear programming problems are the problems where we have constraints as well as the objective function in the form of linear equations. That is, the power of variables is only unity. And these are called linear programming problems. Simplex method gives us a solution to the problems having objective function of maximization nature and constraints are all less than nature. And these kind of problems can be solved using simplex method. I would say simple simplex method. But we face some problem when we have objective function of minimization nature and the constraints are of greater than or equal to nature. And there we have some problem in using the ordinary simplex method. So there is a difference in solving the problems where have objective function as minimization and the constraints are of the nature of greater than or equal to. Today we will see how to solve these kind of problems and what are the problems we face if we use ordinary simplex method. In ordinary simplex method, I said problems of maximization nature and the constraints of less than equal to nature are used. In the constraints where we have the inequality sign of less than equal to and this sign is removed to equality by use of slack variables, and these slack variables are positive in nature and the sign for these is also positive in the equations. In any LPP or simplex problems, we have all the variables as well as the slack variables positive in nature. Positive in nature means greater than equal to 0, and this is a non-negativity constraint in the problem and that exists in all our problems, whether it is the problem is of minimization nature or maximization nature and the signs are greater than or equal to. We use all these non-negativity constraint, but when the problem is of the nature of maximization and the constraints are less than equal to. I will give you an example. Suppose we want to maximize the profit, that will come in our objective function and there is a restriction on the resources. So that restriction is written in the form of less than equal to sign. Before using the simplex method, we have to introduce slack variables in the equations to convert the inequality sign to the equality sign, and these are added to the equations. Each surplus variable is added rather each slack variable is added to the equations, so that on the left hand side, when we say that left hand side is less than equal to the right hand side, it means something should be added to the left hand side to make it equal to 0, and that thing which is going to be added will be positive in nature, means non-negativity constraint exists, and this is in the form of slack variable. Now, consider the problem of constraint which is of the nature of greater than equal to, then we have a problem. We cannot have slack variable because the left hand side is greater than the right hand side. If it is greater than the right hand side, then something should be subtracted from the left hand side to make it equal to the right hand side. Now, this will have a negative sign if we introduce any variable in the form of slack variable, and that will have a negative sign. If it has a negative sign, if we put the equation equal to 0, then that slack variable which has been added will be negative in nature. That defeats our requirement of finding a solution to the LPP problem. So, this is the problem which we face when the inequality sign is of the nature of greater than equal to. So, what should be done then? So, we have come up with a method which is called Big M method, and I shall be demonstrating what are the problems and how to come over these problems and find a solution to the problem. Up to this point, we have seen constraints of less than or equal to variety. Problem is with constraints of greater than nature. Let us have an example of an equation, and the equation is 5x plus 3y greater than equal to 100. X and y are two variables, and then we have inequality sign which is greater than equal to. Left hand side says only 5x plus 3y, right hand side says 100, and the sign in between is greater than equal to. And if I say 5x plus 3y minus s minus t is equal to 100, and s and t two are added, assuming that there will be two equations. Each equation will be having a surplus variable, one equation having s, the other equation having t. In one equation, the coefficient of one variable will be 1 and the coefficient of second variable will be 0, because only one slack variable will be possible. Now, let us assume this is the equation 5x plus 3y minus s minus t. While finding its initial solution, we will have to put it equal to 0. The moment we put it equal to 0, then s and t both will be negative in nature. So, we cannot have this situation because s and t are positive values, and non-negativity constraint exists for s and t also. So, we cannot have the same similar solution what we saw in the simplex method. So, we should have something new for these kind of problems where we have inequality sign of greater than equal to 0. And then we have so far solved maximization problems. Where we have minimization problem, the same procedure cannot be followed, then we should have a different procedure. Mathematically also, we should learn what the mistake is there and what the problem is there while using the simple simplex method. And we shall be having a new method which is called Big M method for solution to these kind of problems. Mathematical explanation to the problem is if in a starting simplex tabular, we do not have any identity submatrix, that is an obvious starting basic feasible solution. So, initially if in the equations we do not find basic feasible solution, then we introduce artificial variables to have a starting basic feasible solution. This is known as artificial variable technique also. There are two methods to find the starting basic feasible solution and solve the problem. And these two methods are, the first one is the big M method and the second one is two-phase method. In this lecture, we discuss the big M method only. Now, I think the viewers must have stood the problem. Now, suppose a constraint equation I does not have a slack variable. That is, there is no ith unit vector column in the left hand side. Let us concentrate on the left hand side. And there is no ith unit vector column in the left hand side of the constraint equation, which means that this happens, for example, when the ith constraint in the original LPP is either greater than equal to or just equal to. Then we augment the equation with an artificial variable Ri to form the ith unit vector column. So, we want some vector and that is introduced by a variable called Ri. However, as the artificial variable is extraneous to the given LPP, we use a feedback system. Rather, we use a feedback mechanism in which the optimization process automatically attempts to force these variables to zero level. This is achieved by giving a large penalty to the coefficient of artificial variable in the objective function as follows. Now, we will follow the procedure. Artificial variable objective coefficient, we said artificial variable is there, Ri is the artificial variable, and the coefficient of this variable is m. M is a very large number, that is why the name of this procedure is also big M. Now, we use minus m as well as plus m. Minus m is used for maximization problem and just m means positive m is used for minimization problem, where m is a very large number. Let us have an example. I think viewers are advised to concentrate on the slide to understand the procedure of this big M method. Problem, a very simple problem in the initial stage we are taking. This is of course not of minimization problem, this problem is of maximization, and the objective function is to maximize z, which is equal to 2x1 plus 3x2 minus 5x3. In this equation, we see that there are three variables and these are related like 2x1 plus 3x2 minus 5x3. There are two constraints also attached to this objective function, and the first constraint is x1 plus x2 plus x3 is equal to 7, and the second constraint is 2x1 minus 5x2 plus x3 greater than equal to 10. Now, look at this problem, and this problem has unique features in the form of unique constraints. Unique in the sense what we have studied in the past in the normal simplex problems, these constraints, the first one is just equal to and the other is greater than equal to, whereas we have studied so far constraints of less than equal to sign, and we solved the problems with simplex method. Now, these kind of problems, how to solve them? The method is big M method, and I am going to demonstrate how to use this method. Basically, we understand the objective function, we understand the constraints. Of course, non-negativity constraint is also there, which says that x1, x2 and x3 all are greater than equal to 0. They cannot have negative values. Now, introducing surplus and artificial variables. S2, R1 and R2, the LPP is modified. The earlier problem is now going to be modified by introduction of surplus variable and the artificial variable. How these are to be entered in the earlier equations, I am going to demonstrate. And the problem is of maximization nature. So, I have written maximize what? Z is equal to 2x1 plus 3x2 minus 5x3 minus mr1 minus mr2. R1 and R2 are artificial variables, whereas m is a very big number. Subject to the constraints are also modified now by the introduction of surplus variables. x1 plus x2 plus x3 plus r1 is equal to 7. 2x1 minus 5x2 plus x3 minus s2 plus r2 is equal to 10. Now, just concentrate on these two equations which are showing the constants. The first equation has only artificial variable and no surplus variable. Why is it so? Because the sign was only equal. There was no inequality sign. So, there is no requirement of introducing any surplus or any slack variable. The other constraint was of greater than equal to nature. This is the second equation, and look at the second equation. The second equation says that it is 2x1 minus 5x2 plus x3 minus s2 plus r2 equal to 10. In this particular equation, we have introduced surplus variable in the form of s2. Because it is in the second equation, that is why it is s2. If it were in the first equation, we would have written s1, and there is no point in discussing why s1, s2, any surplus variable has been chosen. Now, the point to be discussed is, first, the name of this variable is called surplus, and it has a sign before it as negative sign. What is the reason for that? Because the equation had inequality sign in the form of greater than equal to. When the left hand side is greater than the right hand side and we want to make it equal to, it means we should subtract something from the left hand side, then it will become equal to the right hand side. That is what we have done. And when the situation is like this, that left hand side is greater than the right hand side, so something is surplus in the left hand side as compared to the right hand side. That is why the name surplus has been selected. Earlier in the problems where we had non-negativity sign of, rather inequality sign of less than equal to, left hand side was supposed to be less than the right hand side. It means something should have been added to the left hand side to make it equal to the right hand side. Then we used to add slack variables. They had positive sign before them. That is the explanation for negative sign in this surplus variable. The name is surplus, and they are also called negative slack variables because the sign is negative, and they are negative in nature as compared to slack variables. Now, looking at the equations, we find that basic feasible solution with these kind of equations is possible. That is why we have introduced this method to overcome the problem what we stated in the beginning. Now, what exactly is to be done next, I am going to explain. Now, we solve the above LPP by the simplex method. Once again, I want the viewers to concentrate on this particular slide. to understand the basic things which are being used for the big M method. Basic things we have introduced which are unique to this method, and these are other than the technique which was used in simplex method. Here we have a difference that our objective function is of maximization, not of minimization. That is why we introduce artificial variables in the objective function, as shown in the equation z is equal to 2x1 plus 3x2 minus 5x3 minus mr1 minus mr2. Just concentrate on this equation. R1 and R2 are artificial variables and m is a very big number. Now, subject to the constraints x1 plus x2 plus x3 plus R1 equal to 7. There is no surplus variable added in this equation because the sign was only equal to, it was not inequality sign. That is why no surplus or slack variable is required in this equation. The second equation 2x1 minus 5x2 plus x3 minus s2 plus r2 is equal to 10. In this equation, the inequality sign was of the nature of greater than equal to. That is why the variable which is called surplus variable s2 has been added, and it is negative in nature. So, this is a procedure to use as a big M method for the problems of the nature of maximization and then finally constraints having either equal to sign or having greater than equal to sign. So, this is the initial job to be done before further solving the problem. Now, look at the objective function equation 2x1 plus 3x2 minus 5x3 minus mr1 minus mr2. And in this equation R1 and R2 are artificial variables, and our first aim and the first step is by somehow we should be getting rid of artificial variables in the initial state. R1 and R2 are to be removed from this equation. So, how these are to be removed? We will go to the constraints and find out the values of artificial variables, and we will put those values in the objective function and we will get rid of R1 and R2 which are artificial variables. Now, objective function which says that z is equal to 2x1 plus 3x2 minus 5x3 minus mr1 minus mr2 can also be written like z minus 2x1 minus 3x2 plus 5x3 plus mr1 plus mr2 equal to 0. So, the first step is to convert the equation which gives us the objective function so that we have 0 on the right hand side. This is what we have done in the second equation, and it is very easy to understand how this can be done. Now, as I said, we are to get rid of R1 and R2 from this equation. What we are going to do? As I said, we will put the values of R1 and R2, and these values we will get from the constraint equations. The first constraint equation which says that x1 plus x2 plus x3 plus R1 is equal to 7, and this can be written as R1 is equal to 7 minus x1 minus x2 minus x3. Very simple. Everything has been taken to the right hand side except R1. So, R1 will become equal to 7 minus x1 minus x2 minus x3. This is the first equation which gives the value for R1, and similarly we have to do it for R2 also from the second equation. And second equation we have surplus variable in the form of S2. 2x1 minus 5x2 plus x3 minus s2 plus r2 is equal to 10. Simply we have to take all the terms on the right hand side except r2 so that we get the value of r2. So, r2 in that case will be 10 minus 2x1 plus 5x2 minus x3 plus s2 equal to 10. So, now we have value for R1, value for R2, we will put these values in the equation giving us the objective function, and this is the converted equation, rather second equation. In this equation, we will put the values of R1 and R2, so that we get rid of R1, R2 from our problem. So, how to do it? We will repeat z minus 2x1 minus 3x2 plus 5x3 plus mr1 plus mr2 is equal to 0. This is our basic equation showing us objective function. This equation shows that R1 and R2 are present. From the equations which give us the value of R1 and R2, we will put the values of R1 and R2 in this particular equation, and we will get z minus 2x1 minus 3x2 plus 5x3 and plus m within the brackets, which is the value of R1, 7 minus x1 minus x2 minus x3 bracket close plus m into within brackets, which is the value for R2, 10 minus 2x2 plus 5x2 plus x3 plus s2 bracket closed equal to 0. We have done nothing but we have put the values of R1 and R2 in the equation which gives us the objective function. Now, we will simplify. After simplification, we get z minus 2x1 minus mx1 minus 2mx1 minus 3x2 minus mx2 plus 5x2 plus 5x3 minus mx3 minus mx3 plus ms2 plus 7m plus 10m, and then of course, this equal to 0. Left hand side we have lot many terms, on the right hand side we have 0 only. Again further simplification, we will get z plus within brackets minus 2 minus 3m bracket closed x1, and next plus within brackets minus 3 plus 4m bracket closed x2 plus 5 minus 2m bracket closed x3 plus ms2 equal to minus 17. Why minus 17? Because on the left hand side we have 7m plus 10m. 7m plus 10m is 17, and this is positive in nature. When we take it on the right hand side, the sign will change to negative. That is why it is 17m. I will repeat the final equation. The equation is z plus minus 2 minus 3m x1 plus minus 3 plus 4m x2 plus 5 minus 2m x3 plus ms2 equal to minus 17m. So, this is the objective function equation rewritten. Till now, we have a different procedure as compared to our simple simplex method, and this is to be introduced only to get rid of the problem of non-negativity which were coming in our solution if we solve it by a simple simplex method. The problems which are having constraints with greater than equal to sign, and sometimes having objective function also minimization nature. So, this or rather these steps are to be performed before we use the simplex method. After this, we shall be using the simplex method to find the solution to the problems. I am going to demonstrate on this particular problem how to use the simplex method to get a solution. So far what we have done, again I will repeat, our problem was of maximization, but our constraints, one constraint was of equal to and the other constraint was greater than equal to sign. So that we should not have any problem of non-negativity, and we have changed the procedure a little bit, and now finally we have objective function in the form what we wanted. and this can be now used to solve the problem, and we shall be using first simplex method. This particular table, what we used to do in the simplex method, all those steps have been taken into account. First row gives us basic variables, starting with objective function z for the first column, and next is variables x1, x2, x3, s2, r1 and r2, last column is solution. Variables are x1, x2, x3, s2 and r1, r2. The second column shows the z, and the last column use the solution. And now nothing but we have transferred the coefficients of the equations in the first row, second row and third row. Basic variables in the first column z, r1 and r2 are written, and the coefficients are dropped. Z, initially we had 1, minus 2, minus 3, 5, 0, m, and finally 0. And the R1 row has 0, 1, 1, 1, 0, 1, 0, 7, and R2 has 0, 2, minus 5, 1, minus 1, 0, 1 and 10. Viewers must be wondering from where these variables have come. These variables have come from the previous slide. I will go back to the previous slide. Okay, from here these variables are come, where we have changed, say R1, 7 minus x1 minus x2 minus x3 from these equations, and the z equation z minus 2x1 minus 3x2 plus 5x3 plus mr1 plus mr2. From here for x1 minus 2, for x2 minus 3, for x3 plus 5, for r1 m and r2 m. These coefficients have been transferred to the next table. Now I will go to the next table, and these are now transferred coefficients. First three equations are just nothing but the transferred coefficients from the previous equations, and we can have a look also. Again, r1 is 7 minus x1 minus x2, and these are coefficients which have been transferred to the r1 row and the r2 row, and from the basic constraint equations only these have been transferred. And we converted the objective function equation, removing the r1 and r2, and that equation was nothing but which has been given in the bottom. First value is coefficient of x1 in the z row, and that has been added here under x1, because x1 had a coefficient of minus 2 minus 3m, that has been written under x1 column. And similarly for x2, this has been added, minus 3 plus 4m has been added in the column which has a variable x2. So I am showing from where these coefficients have come, and this equation was after removing r1 and r2. For x3 also the coefficient is 5 minus 2m x3, and that is why it is written 5 minus 2m x3. And ms2, for s2 also m has been written. Okay. And then finally 0, 0, because r1 and r2 have already been removed and they are not present in the equation, that is why their coefficients are 0. For r1 and r2 coefficients are 0. And in the solution part, of course, minus 17m is there, that is what is written here, minus 17m. So this is a way how to transfer the coefficients, for the z equation, how to transfer the coefficients for r1 and r2. This has been done and this has been explained also. Now the steps are to be carried out are, we have to find out, as in our simplex method, which is the pivot column. Just see, which is the pivot column? Pivot column is the column having the variable x1. Okay. And then finding out the pivot row, we have to concentrate on the first two rows having R1 and R2. R1 and R2, these are the values 1 and 2 and the solution values are 7 and 10. We have to find out the theta value. Theta value is obtained by dividing the solution, which is 7 in the first R1 row, by the element 1, which is present in the pivot column. 7 by 1 is 7, and then finally the second row R2. R2, the solution value is 10, 10 is to be divided by the element 2, 10 by 2 is 5. And then we have to find out the pivot row also. Pivot row is the row which has the minimum theta value. The first value was 7, the second value was 5. 5 is for the R2 row, and so R2 is the pivot row. So, what is the next step to be carried out? I will repeat again simplex method. First table is formed as shown in the slide. This table will look for values in the Z row. Okay. In this particular case, the maximum negative value is to be chosen, and the maximum, if we look at the elements, the Z row first is 1, second is minus 2 minus 3m, next is minus 3 plus 4m, next is 5 minus 2m, then m, then 0 and then 0. Out of all these values, minus 2 minus 3m is the most negative value because m is the big number and it has a negative sign, and other big number with the negative sign is minus 2m. So, minus 3m has a most negative sign. So, that is why this is the column which is called the pivot column. Now, finding out the pivot row, we have to see the R1 row and R2. We have to find out the elements in this particular column, and the elements are 1 and 2, and we have to divide the solution elements 7 by the corresponding value 1 and the solution value 10 by the corresponding value 2. So, 7 by 1 is 7, 10 by 2 is 5. Out of these 7 and 5, we have to choose the minimum value. Minimum value is 5, 5 is for the R2 row. So, R2 row is called the pivot row. Where this pivot column and pivot row cross, that is the pivot point. That is the pivot. So, now we have come to know that pivot is 2, and the next step is all the elements are to be divided by this pivot value. So, 0 is to be divided. So, first value is 0, we will divide the 0 by 2, we will get nothing but 0. We will divide 2 by 2, we will get 1 as shown in the last row, and I am calling it R2 row. Okay. And then again next minus 5 is the element which will be divided by the pivot value. Pivot value is 5. So, we will get minus 5 by 2, and again 1 is to be divided by 2, we will get 1 by 2. The next is minus 1, which is going to be divided by 2, we will get minus 1 by 2. So, 0 divided by 2 is 0, 1 divided by 2 is 1 by 2, 10 divided by 2 is 5. So, our revised row is R2 0, 1, minus 5 by 2, 1 by 2, minus 1 by 2, 0, 1 by 2 and 5. Now, the viewers will understand which is the entering variable and which is the leaving variable. See the slide, and you will find that x1 is the entering variable and R2 is the leaving variable. So, instead of R2 in the row, we will write x1. We will write x1. So, x1 is the entering variable, R2 is the leaving variable. Whatever value we have here, that is assigned to x2. So, next step is we have to convert 1 and 2. We have to convert 1 and 2 to 0. We have to do some operation on the row where it is R2 row, actually now it is X2 row, some operation on this row and the corresponding row on R1 and R2 to bring these values 1 and 2 to 0. So, we will see how the next step is to be carried out. Okay. Now, we will see the operation for Z row. We have to bring this row element to 0, because our pivot is now R2 is 2 and these two values, 1 is to be brought to 0 and -2 -3m is to be brought to 0. How we are going to do it? It is written at the bottom. Operation to be carried out on the Z row, because in the Z row element in the pivot column is to be brought to 0. Multiply all the elements of X1 row by 2 plus 3m and add to Z row. We had R2 row and we will multiply all the elements of this row by 2 plus 3m and add to Z row, because 2 plus 3m, when we multiply 1 by 2 plus 3m, it will be 2 plus 3m, and this is minus within brackets 2 plus 3m. This minus and plus will get cancelled and the net result will be 0, and this way we will bring it to 0. So, I will demonstrate for each such cell value and how these are carried out. X1 row is 0, 1, minus 5 by 2, 1 by 2, minus 1 by 2, 0 and 1 by 2 and finally 5. This is nothing but the R2 row. This is nothing but the R2 row and where it has been divided by 2, and now R2 has been removed and X1 has been entered here, and this is now the revised row with pivot as 1. Next, we will do the operation as it is written at the bottom, and how the values are obtained, because the Z row all the values have been entered, and how these are achieved, these are being demonstrated at the bottom. First, I said the operation to be carried out is X1 row is to be multiplied by 2 plus 3m and added to the Z row. So, the same operation has been done, 2 plus 3m minus 2 minus 3m, this brings it to 0. What we wanted, the pivot column, the value of this particular cell should be 0, and this has been done like this. Next, this has been demonstrated. The arrow also, this 0 has been taken to the Z row. Okay, next is look at the Z row. Next element is minus 3 plus 4m. Minus 3 plus 4m, as I am to do, multiply all the elements of X1 by 2 plus 3m, and this is what I am going to do. I am multiplying all the values by 2 plus 3m and minus 3 plus 4m, and finally we will get minus 5, minus 15 by 2m, minus 3 plus 4m and 8 minus 7 by 2 m, and this is nothing but this has been transferred here also in the Z row. Just look at the operation. So, value under X2 and this coefficient is calculated like this. Again I will repeat, the first 0 has been obtained by 2 plus 3m minus 2 minus 3m equal to 0, and for the second element means the value under the X2 variable is minus 5 by 2 within brackets 2 plus 3m minus 3 plus 4m, which is equal to minus 5 minus 15 by 2m minus 3 plus 4m, and then finally we get minus 8 minus 7 by 2m, and this has been transferred to the Z row also. And for 6 minus m by 2, again I am going to demonstrate the operation. Here again I am to multiply the Z row by 2 plus 3m and then finally take it there. So half of it 2 plus 3m, and then plus 5 minus 2m equal to 1 plus 3 by 2 m plus 5 minus 2m, and finally we get 6 minus 1 by 2 into m, and this is going to be transferred to the z row. With the arrow we are demonstrating. And the next, how we have achieved minus 1 minus 5 by 2. Just look at this. Earlier we had only minus half. The equation had only minus half, and into 2 plus 3m plus m, and then it is equal to nothing but minus 1 minus m by 2, and this has been written here also. And we are demonstrating with an arrow also. Minus 1 minus m by 2, and this goes to the z row element. And how we have achieved 0, again it is being demonstrated. 0 has been achieved. 1 by 2 within brackets 2 plus 3m equal to 1 plus 3 by 2m, and this has been written here also. And then finally 10 minus 2m, how it has been achieved? 5 into 2 plus 3m minus 17m, 10 plus 15m minus 17m, the final result will be 10 minus 2m, and this has been transferred in the z row. I think I am able to clearly demonstrate how the z row has been modified. Here we wanted nothing but the value of cell under the x1 variable, which was a pivot column, to bring it to 0. And this has been brought by which method? Multiply all the elements of x1 row by 2 plus 3m and then add to z row. This is what we have done, and finally we have achieved it. Finally we have achieved it also. So again I'll demonstrate, again I'll repeat one by one. The first 0 has been achieved by 2 plus 3m minus 2 minus 3m, which is again equal to 0. And the second is how minus 2 minus 7 by 2m is achieved. Again we have to multiply the z row initial value by 2 plus 3m and then add to it. Minus 5 by 2 within brackets 2 plus 3m minus 3 plus 4m, then it is equal to minus 5 minus 15 by 2m minus 3 plus 4m, then finally it is equal to minus 8 minus 7 by 2m, and this has been transferred to the z row. And similarly 6 minus m by 2 has been achieved by half 2 plus 3m within brackets and then plus 5 into 2m, and 1 plus 3 by 2m plus 5 minus 2m, the final result is 6 minus 1 by 2m, and this has been transferred to the z row. Similarly, for the value under S2 is calculated minus 1 by 2 within brackets 2 minus 3m, rather 2 plus 3m bracket close plus m equal to minus 1 minus m by 2. 0 under the R1, because its value is 0, 0 multiplied by 2 plus 3m is 0, when 0 added to 0 is again it is 0. The last but 1, R2 also is calculated 1 by 2 within brackets 2 plus 3m equal to 1 plus 3 by 2m. This is the result which has been transferred to the z value. And finally 10 minus 2m has been calculated like this: 5 plus 2 plus 3m, because we have to multiply it with 5, because the value is 5. So 5 plus 2 plus 3m minus 17m and 10 plus 15m minus 17m, and then finally we get 10 minus 2m. So this is the way we have converted. This is the way we have converted all the element values to bring only 0 under x1. I said we have to have an operation on the x1 row. X1 row which earlier had pivot was brought to 1 because the earlier row was R2 which had a pivot of 2. When the entire row was divided by 2, this value was converted to 1, and this was R2 was the living variable, X1 was the entry variable, and this was the modified row. X1 was the modified row. So I have to do the operations on this X1 row, and finally we are to bring the value of Z to 0 in this X1 column. So that has been carried out, and next step is the other row also, now other value also we have to bring it to 0, and same operation is to be carried out, rather similar operation is to be carried out, and we shall be bringing the value of the element under X1 column as 0. If we repeat the same, we will get these values, Z value, we will get these values, X1, R1, all these have been converted now. We will have X2 and X1. These three rows we will be getting after doing the second operation in the similar way, the way we did it on the first. So Z objective function value, okay, will be in the last column, which is the solution column. The value is 102/7, and X2 value is 4/7, and X1 value is 45/7. By now, I think viewers will be able to know the answer to this particular problem. Answer to this particular problem is the value for variable X1 is 45/7, value for the variable X2 is 4/7, and value of the objective function is 102/7. This is the solution to the problem, and I have done nothing but use the simple simplex method. Now I am writing the entire problem in a tabular form, and starting from the first step using simplex method, and on the equations which are converted into basic simplex problems, so that we get rid of the greater than equal to sign, and we are able to solve the problem having maximization objective function. First, initially we have to transfer the coefficients as such. R1, Z, R2 coefficients have been transferred like this, initially, and this has already been demonstrated also. And now these R1 and R2 are to be taken out from the solution. We will bring M values, which are the coefficients of R2, 0, and we shall be bringing the solution without R1 and R2 variables. This is the way we have to do. Again, I will demonstrate. First step, what we did, we put the values of R1 and R2 in the objective function, and the coefficients so achieved are written here, and doing so we are able to remove the m's, and m's are taken to equal to 0, and similarly, and these other coefficients are written. And then we have to find out the pivot column and the pivot row, and this is the pivot, and then divide the pivot row by the pivot value, and we get the revised row. R2 is the living variable, X1 is the entering variable. That's why instead of R2 we are writing X1. X1 is now 0, 1, minus 5/2, 1/2, minus 1/2, 0, 1/2, and finally 5. This has already been explained in the previous table, and the way we have done it is also clear to the viewers. And now the Z is now written. Z is 1, 0, minus 8, minus 7 m/2, 6 minus m/2, minus 1, minus m/2, 0, 1 plus 3 m/2, and finally 10 minus 2m. And this has been done to bring the value under the X1 variable against the Z row as 0. And next is R1 row also, we have to bring it to the 0 value, and this has been done, and this is shown also. R1 is 0, 0, 7 by 2, 1 by 2, 1 by 2, 1, minus 1 by 2, and the final value in the solution column is 2. So, R1 still exists, and we have to do the second phase of calculation. Second phase of calculation is we have to find out again the pivot column, and this is the pivot column under x2. Maximum, we have to choose the maximum negative value. M is a very large number, minus 7m, and then minus m, minus m. So, this is minus 7m is the most negative number. So, that's why it has been selected as the pivot column, and the pivot row we have to select, and this is the R1 row is the pivot row. Again, it is achieved by theta values. So, that's why we have to we are calling it as pivot row, and the pivot point is 7 by 2. We will divide all the element values by 7 by 2, and will R1 is a living variable, x2 is the entering variable. Instead of R1 we shall be writing x2, and x2 is now 0, 0, 1, 1 by 7, 1 by 7, 2 by 7, minus 1 by 7, and finally answer in the solution column is 4 by 7. So, viewers must note here R1 was the living variable and x2 was the entering variable. That is why we have replaced R1 with x2, all other values remaining same. Okay. In the Z row, again the step we did in the first phase of calculation, that is the value of the cell under x2 and the Z row is to be brought to 0. That has been brought to 0 as shown in the slide also, and other values are 50 by 7, 1 by 7, 16 by 7 plus m, minus 1 by 7 plus m, and finally 102 by 7 in the solution column. X2 we have already written as 0, 0, 1, 1 by 7, 1 by 7, 2 by 7, and minus 1 by 7, finally 4 by 7 in the solution value. And x1 again is written here 0, 1, 0, 6 by 7, minus 1 by 7, 5 by 7, 1 by 7, and 45 by 7 in the solution column. Looking at this table, which gives us a complete idea of the calculations which was to be carried out in the form of a simplex method to solve our problem. The final solution now, the solution of the objective function is 102 by 7. The value for x1 variable is 45 by 7. Value for the x2 variable is 4 by 7. This completes the solution to the first problem. Now, our solution, the optimum means maximum value of the objective function z is 102 by 7, and coordinates for this objective function are x1 equal to 45 by 7 and x2 equal to 4 by 7. x2 didn't appear in the solution, x3 is 0. So, this is the solution to our problem, and the way we will solve the problem has already been explained thoroughly. I think viewers must have come to know the big M method by now. Okay, now I quickly go through the remarks. The remarks are, if in any iteration there is a tie for entering variable between an artificial variable and other variable, decision, surplus or slack, we must prefer the non-artificial variable to enter the basis. And if in any iteration there is a tie for living variable between an artificial variable and other variable, means decision, surplus or slack, we must prefer the artificial variable to leave the basis. If in the final optimal table an artificial variable is present in the basis at non-zero level, this means our original problem has no feasible solution. So, this completes the big M method. I hope I am able to make it clear to the viewers how to use big M method to solve a particular problem with a different nature as compared to the simple simplex problems.
With this note, thank you, sir. Thank you so very much for delivering such a nice lecture, and I hope that in future lectures also we would be learning more on the operations research. Thank you.
Thank you.